Here we are on page 3 of functions addendum. Solve for x. So let's take this first one here. Whenever you're solving an inequality like this, the best thing to do is to make a sign diagram, which is basically a number line indicating at what values of x the left-hand side becomes positive and when it becomes negative. So let's do that. So this one, what are the critical points for this? Well, if I put a 2 here, that would make the whole thing equal to 0. If I put a negative 3 here, it would make the whole thing equal to 0. So those would be my 2 critical points. I'm going to draw my number line here. I'm going to put both my critical points on here, 2 and negative 3. And both of those cause the function to become 0, so I'm going to mark those both 0. And then I'm going to use the in-between values such as 0 and maybe like 10 and maybe negative 10 to figure out what would be the value of the left interval, the right interval, and the middle interval. So let's put in negative 10 first. If we put negative 10 first, we would get 2 minus negative 10, which is 12, and then we would get negative 7. So we would have a positive number times a negative number. That would be a negative value. And do you notice when we put in negative 10, we get a negative value? What if we put in any other number in the interval, like negative 9 or negative 5 or negative 1,000,000? Those would also all give you negative numbers. How do we know that it would never give you a positive number within this interval? Well, we've already found the 2 critical points, the ones that make the function equal to 0. And those would be when the function crosses over from a negative region to a positive region. So since there are no critical points to the left of negative 3, we know that all the points left of negative 3 are going to be all negative or all positive. So all we need to do is test one point, like negative 10. If we discover that negative 10 yields a negative number, then all the x values left of negative 3 are going to yield a positive or a negative number also. Okay? Let's try 0. If we put 0 in there, we get 2 minus 0 times 0 plus 3, which would be 2 times 3. Which is a positive number in the middle. What about if we put positive 10? 2 minus 10 is a negative number. 10 plus 3 is a positive number. Negative times positive is negative. Okay. So basically we have these 3 intervals, negative, positive, negative, with the critical points negative 3 and 2 being the dividing boundaries of those 3 intervals. Okay, let's move on to E. X squared is greater than or equal to 3x. Okay, so in this case, first we would want to rearrange it so that we have 0 on the right side. So let's subtract 3x from both sides. And then we'll have x squared minus 3x is greater than or equal to 0. We'll draw our number line. What are our critical points? Let's factor this to find our critical values. We're going to factor out an x. Okay. So if we put a 3 here, that would make the whole... No, if we put a 0 here, that would make the whole thing 0. If we put a 3 here, it would make the whole thing equal to 0 also. So our 2 critical points are 0 and 3. And now we just need to test points in between to figure out if the intervals are positive or negative intervals. So let's put in a big negative number, like negative 100. We'll have negative 100 times negative 103. 2 negative numbers times each other would be a positive number. So the negative 100 region, or left of 0, would yield positive numbers. What about a number between 0 and 3, like 1? 1 times 1 minus 3 is 1 times negative 2, which is a negative number, so the middle interval is negative. And then we'll put in a big positive number, like 100, so 100 times 97 is a big positive number, so this would be positive too. And I didn't give the value of x here. What I need to do here, since it says greater than or equal to 0, the values of x which would satisfy this equation would be x is between negative 3 and 2. Now, would I put less than, or would I put less than or equal to? Let's see. Well, if we want to be greater than or equal to 0, we need to include these 2 light green shaded points also. So we do need to include negative 3 and 2 in the interval. What about for this next one? So we're going to have, we want greater than or equal to greater than or equal to 0, right? So that means that we want to include the positive regions, which are the left and the right regions, and we want to include the critical points 0 and 3. So we're going to say x is less than or equal to 0, and x is greater than or equal to 3. There would be two parts to that interval. Okay. C. First, we have 0 on the right side already. So now we just need to figure out the critical points. This would be a 3. This would be negative 1/2. And let's mark those on the number line. So we got 3, and we got negative 1/2. And let's test some points in between to figure out if the intervals are positive and negative. So we'll put in a big negative number like negative 100. That'll give us a big negative number times a big positive number because it's minus x. So we'll have a negative number times positive number. That's a negative, so this part will be negative. Then if we put in 0, which is between negative 1/2 and 3, we would get 1 times 3, which is a positive number. And then the right interval, if we put a big positive number, we would get big positive number times big negative number, and that would be negative. Okay, so in this case we want positive numbers, and we would not include the boundaries because we want it to be greater than 0, not greater than or equal to 0. So in this case we'll say that we want the interval of x between negative 1/2 and 3. Okay. And then x squared is less than 4. So x squared is less than 4. So in this case, we would like to have 0 on the right side. So let's subtract 4 from both sides. And then we'll have x squared minus 4 is less than 0. And then we're going to factor the left side so we can find the critical points. X squared minus 4 factors into x minus 2 times x plus 2. And then we're going to draw our number line. Where I'm going to put it here. The number line will have two critical points. It'll have negative 2 and it'll have positive 2 because here here positive 2 is the critical value and here negative 2 would be the critical value. Those would make the whole thing equal to 0. And then we'll mark those 0, and then we will test different points on the interval. Like, for example, 0. We'll put 0 in there. We'll get 0 minus 2 times 0 plus 2. Negative times a positive is negative. Then we'll put in a big positive number. So a big positive number will give you a big positive number times a big positive number, which will be a positive number. And then I'll put a big negative number. A big negative number times a big negative number is a positive number. So in this case, what are we looking for? We're looking for values of the function that are less than 0. So we would want actually this interval here, which is when it's negative, and we would not include the critical values because the critical values make it 0, and we want it to be less than 0. So in this case, we would say x is between negative 2 and 2. Okay, let's go to K. Same thing here. We already have 0 on the right side, so we're going to factor the left side. Maybe 2 and 2. 2x minus 1 times 2x minus 1. Does that work? Yes, it does. Okay. So, and the critical values here would be positive 1/2 and positive 1/2. So there would be two critical values at the same point of 1/2. So I'm going to mark that 1/2. And what happens when you have two critical values or two roots at the same point? Usually what happens is we have that nice alternating pattern of plus minus in all the other problems up until now. But on this problem, we're probably going to have both plus or both minus. Okay? So let's see. Checking numbers to the left of 1/2, like negative 100. If we put negative 100 into 2x minus 1 times 2x minus 1, we're going to get a positive number. And if we put in a big positive number like 100, we would also get a big positive number times a big positive number or a big positive number. Okay? So we would get positive on both sides. So when is this function less than 0? It's less than 0 nowhere. So basically the solution is the empty set. Okay? which you can write either that way or that way. Or you could write no solution, something like that. Okay, x squared plus 4x plus 4. Again, we're going to factor x plus 2 squared is greater than 0. So a negative 2 value here would make it equal to 0. So I'm going to draw my number line with negative 2 as a critical point. And now I'm going to put in a big negative number in here, and I'll get a big negative number squared, which is a positive number. I'll put in a big positive number. Big positive number squared is positive. So the question is, when is this function greater than 0? It's greater than 0 all the time except for at negative 2. So we're just going to say when x is not equal to negative 2. When it's not equal to negative 2. Okay? All right. Let's move on to the next one. So now we have 3x squared on the left, and we have 8 times x plus 2 on the right. Remember that we want the right side to be 0. So let's subtract everything over to the left side, and we'll have minus 8x plus 2. And then we'll have greater than 0. And let's distribute the 8 to the x and the 2. We'll get 3x squared minus 8x minus 16 is greater than 0. And now we're going to factor the left side so we can find the critical points. So it's going to be 3x and x, and maybe 4 and 4. Let's see if that works. So that would give you 4x minus 12 in the middle, which works out to be negative 8, so that's perfect. And then we'll put the greater than 0. The critical points are going to be negative 4/3. And this one is going to be 4. So we're going to put those on the number line, 4 and negative 4/3. We're going to test numbers in the interval, like 0, for example. If we put 0 in this equation, we'll get 4 times negative 4, which is a negative number. If we put a big number like 100 in there, we'll get like 300 times 100, which is a big positive number. If we put a big negative number, we're going to get a big negative number times a big negative number, also positive number. Then we're going to look back and say, okay, what are we looking for? We're looking for greater than 0. So greater than 0 happens here and here. Do we include the critical points 4 and negative 4/3? No, because it's greater than 0 and not greater than or equal to 0. So we can now give the intervals in an inequality. We'll say it's x is greater than 4 and x is less than negative 4/3. Okay. Then we go to Q. Let's move everything to the left side like we've been doing, leaving 0 on the right. So we'll have 12x squared minus 5x minus 2 is greater than or equal to 0. Let's factor this so that we can figure out what the critical values are. Let's see, 2 and 1, 3 and 4. Okay, so that would give us, let's see, let's put a negative here and a positive here. Does that work out? Yes, it does. Okay, so in this case, the critical values are 2/3, and this one is going to be negative 1/4. And I'm going to mark these on here. So negative 1/4, 2/3, and in between the two we got 0. If you put 0 in there, you'll have negative 2 times 1, which is a negative in the middle. And then if you put 2 big positive numbers, you'll get positive out. If you put 2 big negative numbers, you're going to have 2 negatives multiplied times each other. You also get positive out. So, and now we're going to look at what do we want in the solution here. We want greater than or equal to 0. Greater than or equal to 0 would be here and here, including the critical points. So let's write the intervals. We would say x is greater than or equal to 2/3, and we would say x is less than or equal to negative 1/4. Okay. And, let's put everything on the left. 6x squared minus 5x plus 1 is less than or equal to 0. We're going to factor maybe 3x and then 2x here. Yep, that works out, right? And the critical values are going to be positive 1/3, positive 1/3, and 1/2, right? Okay, and then we're going to put those on the number line, 1/2, and then, oops, 1/3 is actually less than 1/2, right? And then we'll check big positive numbers multiplied together gives us positive, big negative numbers gives us positive. And then in between 1/3 and 1/2, what's the value between 1/3 and 1/2? Maybe like, let's see, let's see, 2/5? Oh my God. Isn't there anything nicer than that? Let's see. 1/3 is 0.33. 1/2 is 0.5. What about like 0.4? That's a good one. Okay. So 0.4, we'll test 0.4. So 3 times 0.4 is 1.2 minus 1. And 2 times 0.4 is 0.8 minus 1. So this would become positive. 1.2 minus 1 is positive. And 0.8 minus 1 is negative. So the middle part would be negative. And remember, there's usually a nice pattern like plus minus plus or minus plus minus. So this looks like it's right also. So we are looking for something less than or equal to 0. So basically we want this interval here, including the critical points, because that's when it's equal to 0. So we're going to say that x is between 1/3 and 1/2, and it includes the two boundaries. Okay. Okay, 2a. So here we have x plus 4 divided by 2x minus 1. This is a rational function. To find the critical points for a rational function, we need to find the vertical asymptotes. We need to find the x-intercepts. Remember, to find the vertical asymptote, you just find out when the denominator equals 0, which is when x equals 1/2. So that's one of the critical points. It happens to be the critical point that has the asymptote. To find the x-intercepts, which are the other critical points when it's 0, remember that you make the numerator equal to 0. So x plus 4 is equal to 0 tells you that x equals -4 is the critical point in the numerator when the whole thing becomes 0. Okay? So now we just need to test the intervals in between. So we could put in a big negative number. If we put in a big negative number, we have a negative number divided by a negative number, which is a positive number. If we put in a big positive number, we get positive number divided by positive number, which is a positive number. And if we want to test a value between -4.5, I suggest 0. That's a good convenient point. We would have 0 plus 4, which is 4, divided by 0 minus 1, which is -1. 4 divided by -1 is -4, which is negative. Okay, so there's our interval for this rational function. If we want to give the interval where x is greater than 0, it would be here and here, and it would not include the critical values, because the critical values, at the critical values, it's exactly equal to 0, and we want it to be greater than 0. So let's put here the intervals. X is greater than 1/2, and also x is less than -4. Okay, let's go to the next one. 2 over 2x minus 5 is less than 1 over x plus 7. Let's multiply, do a cross multiplication to get everything out of the denominator. Okay. And you notice that when I multiplied each side by the opposite side's values, like I might multiply both sides by 2x minus 5, I multiplied both sides by x plus 7, I didn't really pay attention to the fact that maybe these expressions, 2x minus 5 and x plus 7, are negative values. And if they're negative values and I multiply by negative values, then I need to be careful about inverting the inequality, right? But the first thing I'm going to do is I'm going to assume that both values are positive and see what happens, okay? So if I assume that both values are positive and I distribute the 2 here, and then this one is going to be 2x minus 5. Now I'm going to simplify this. I'm going to put both x's on the left side. But you notice that if I subtract 2x from the right side and subtract 2x from the left side, I don't have any x's anymore. And then I would end up with 14 is less than negative 5, which is an untrue statement. So this is the case where, what was I assuming? I was assuming that both x plus 7 is positive and 2x minus 5 is positive. So if both of these are positive, then I end up with this case where the solution is the empty set. Okay? Now let's try to think about the case where, let's see, I'm going to simplify these a little bit. So x plus 7 is greater than 0 is the same as x is greater than negative 7, right? 2x minus 5 is greater than 0 is the same thing as x is greater than 5/2. Okay, so these are the two conditions we're looking at, which may flip the inequality. Now, if both of these are positive, then we saw that the solution is the empty set. Now let's take the case where both of them are negative. So if both of them are negative, then you end up flipping the inequality twice. The first time you flip it is when you multiply by x plus 7. The next time you flip it is when you multiply by 2x minus 5. And if you flip it twice, then you end up with the same expression as you got before, and then we know the solution is the empty set. Okay? So, the second condition where both x plus 7 is less than 0 and 2x minus 5 is less than 0. And let's simplify that. We'll write it in the way we simplified to. So if x is less than negative 7 and x is less than 5/2, then we know that the solution is also empty set because the inequality flips to the left and it flips to the right, and then we end up with the statement 14 is less than negative 5, which is impossible again. Okay, so this is the second condition. And finally, the third condition would be if only one of them is positive and the other one is negative. Now, when would that happen? Well, x could be, let's see, less than 5/2, but not less than negative 7. So let's say x is less than 5/2, but x is greater than negative 7. Okay? So if x is less than 5/2 and greater than negative 7, I'm going to rewrite that like this. Then we know that then we know that it flips the inequality once, and then instead of 14 is less than negative 5, we'll have 14 is greater than negative 5, which means it's always true. So in the case that x is between these two values, then we know that the inequality is always true. Always true. And if the inequality is always true, then basically we've discovered our answer for when it's true. Whenever x is between negative 7 and 5/2, then it is true. Since this problem is so hard to understand, I just want to show you that by graphing it on the calculator, it's actually a pretty simple problem. It's just that when you do it algebraically, it's kind of weird. So first what I'm going to do is I'm going to show you like the two graphs graphed on top of each other. I'm showing you the interval negative 7 to 5/2. This point here is about negative 8, and this point here is like 2 or 3. So you can see that this is the 1 over 1x plus 7 function, and the 1 over x plus 7 function is indeed above the bottom 2 over 2x minus 5 function during this interval. Now you can see that this function is actually below at this point, right? And then as you when you reach the 5/2 x equals 5/2 point, then this function actually has a piece that's above here. Okay, so these are two hyperbolas next to each other, and you can see that the right side is consistently higher in this interval. So I just wanted to show you that if you graphed it on a calculator, that's another way of solving it if it was a calculator part of the exam. Okay. All right, let's go to E. Okay, again we have a rational function, and I am going to graph this one on the calculator also. Just to show how you would do that, here is the last function that I graphed on the calculator. I'm going to clear out the last function and clear out the other function. I'm going to put the left side on top. I'm going to put the right side on bottom. Best way I think to put in these vertical fractions is as a vertical fraction. So you have a math number, click up to n/d, and then on top you're going to put 2x minus 3, and on the bottom you're going to put x plus 2, and then for y2 you're going to put the right side, which is math, number, n/d, and you're going to put 2x on top, 2x, and on the bottom you're going to put x minus 2, x minus 2, and then you're going to graph it. Oh, and let's change the window size to the regular window size. Hold on a second. Reg window size, or zoom, let's change it to zoom standard, which is like zoom standard. Oh, there it is, number 6. Zoom standard makes it go back to -10 to 10, -10 to 10. So this is the function, this function, because it's got the asymptote of -2. This other function, this function here, has the asymptote of 2, so that would be this one. So which one is higher? Let's see. Well, it looks like the x minus 2 function, the denominator that has x minus 2, is higher here. And then this function is higher on the left side. So basically on the right side, 2x over x minus 2 is higher. The place that is the dividing line is probably, or one of the dividing lines is here, the asymptote here. Okay, so like anything to the right of this asymptote, this hyperbola is taller or higher, right? So this asymptote, remember, is x equals 2 asymptote. So one of the solutions is that the x equals 2 asymptote function, the right side is higher when x is greater than 2. Okay, so x is greater than 2 is part of the solution looking at the calculator. And then like the minute x is less than 2, then the function, the right side function is actually lower than the left side function, right? Up until it gets to this intersection here. And that is when the right side function stops or starts being higher again. So let's figure out where this intersection is. We can do that by doing a second calc. And then we'll do an intersection, intersect, and then say first curve, second curve. Just hit enter twice because there's only 2 curves, and then we put the cursor somewhat close to the intersection of the curves, and it will tell me that the intersection is at 0.545. Okay, so at 0.545, that's this point here. This function is higher to the left of 0.545, so it would be kind of like when x is less than 0.545. And then it would be fine, it would be taller until it got to this asymptote. This asymptote, when it hits this asymptote, this is when the left side function really starts being bigger. So this asymptote, remember, is at x equals -2. So we're going to put the other asymptote here. And so those are your 2 intervals. I really wish that this calculator was a color calculator, because with a color calculator it's a lot easier to see what's going on. You can't see which function is which here, right? So those of you who bought the color TI-84, congratulations to you, because that's really going to help you on your graphing. For those of you who got the black and white, you're just going to have to be that much better at math, okay? So let's take a look at this. I colored this function green and this one red. So we want to know when the green function is taller or higher than the red function. I redrew these functions here in red and green so you can see which one is the red function, which one is the green function. Now we can obviously see that the places where the green function is taller are, let's use the highlighter. It's basically this region here and this region here. Oh, sorry. This region here, but it stops right there. Do you see? So the dividing lines are basically the asymptote position, which is this, and 0.545, which is the x value for the intersection point, which is there, and then the asymptote position once again, which is 2. Okay, so those are the dividing points, and basically you can see that these green regions are described by x is greater than 2 and this interval here. Okay, so this interval here is this part, and this interval here is x greater than 2. Now, does it look like maybe these might cross each other when it gets way out there? Well, the way you can confirm that they don't is you can check the horizontal asymptote for each one. If you find the horizontal asymptote for each one, you'll see that they have both the same horizontal asymptote of y equals 2. And if they both have the same horizontal asymptote, that means they both approach y equals 2, but they never touch it, so they're never going to cross again. So basically our answer is fine. Okay? Let's go to 3a. Solve for x. So in this case, let's first do some algebra and put everything on the left side and put 0 on the right side. Then we're going to factor it. We'll have x squared minus 1 is greater than or equal to 0. Then we'll factor x squared minus 1 using the old SAT rule, x plus 1, x minus 1. And then we're going to put that on a number line. And if we put it on a number line, the critical points are going to be 0, negative 1, and positive 1. And let's check some big values like 100. If we put 100 in there, we're just going to get 3 positive numbers multiplied times each other. That would be positive. If we put a big negative number in there, we're going to get 3 big negative numbers multiplied times each other, which would be a negative. And then if we put like negative 1/2 in there, we'll get a negative. We'll get a negative, a positive, and then we'll get a negative here. So those would be 2 negative numbers multiplied times each other, which would be positive. And then this would follow the pattern here, minus, plus, minus, plus. Okay? So this is the sign diagram for this function. We want to know when this function is greater than or equal to 0. So basically, that would be this region and this region, including the critical points, right? So we're going to say, oh, it's when x is greater than 1, or when x is between negative 1 and 0, okay? Both of those regions are part of the solution. Okay, and finally, let's do 3c. And let's do c now. So, as usual, we're going to move everything to the left side of the equation and leave 0 on the right side. When I do that, I'm going to subtract 2x from both sides. I'm going to subtract 3x squared from both sides. Or I'm going to add 3x squared from both sides. I end up with x cubed plus 3x squared minus 2x minus 6 is less than or equal to 0. And then I'm going to use my calculator to graph this. So I punched in this left side into the calculator, and then I graphed it. And now what I'm going to do is I'm going to find the critical points by using second calc intersect, okay? Once we do the polynomials chapter, then you will be able to maybe do this with synthetic division, or if you remember how to do that from Math 10, maybe you can already. But that's not the point here, so we're just going to do second calc 0. And we're going to use second calc 0 to find all the critical points. Now remember, to find the critical point, you tell the calculator that I'm looking for the 0 intersection between here and here, and then it'll find it for you. So the left one needs to be put slightly to the left of the point you want. Put the right bound slightly to the right of the point you want, and then you say any guess, and it'll tell you that the x-intercept is actually at x equals negative 3. So one of the critical points is at x equals negative 3. Let's find out what this one is here. So this one here is, you do the same thing, second calc 0, you enter, you put the left bound slightly to the left of this point which you want, and then you put the right bound slightly to the right, and then you hit enter, and it will give you opportunity to guess. I am going to guess whatever because I'm already close enough to the one that I want. The whole point of guessing is we have 3 intercepts here, and the calculator doesn't know which one we want. We do the guess and the left and right boundary so it knows which one we want that's close. Okay, and so it tells us that this one is at negative 1.41. Not coincidentally, the square root of 2 is 1.41. And then finally we do the last one also. It turns out this last one is positive 1.41. So now I'm going to show you what the the sign diagram looks like. It looks like this. So I got my values negative 3, 1.41, and negative 1.41 and 1.41 from the graph. Now I can also get the values negative, positive from looking at the graph, right? You can see that the left side is negative, the right side is positive, the second region here is going to be positive, and the third region here is going to be negative. So it has the minus plus pattern. And that's it, okay? And we're done with this page. Thank you for bearing with me.